Hello, everyone. Thank you for joining us tonight. I'm Jim Irwin. I'm the current club president of the NAA. Things are starting to pick up for us a little bit. So these are some of the upcoming events we have. We're back to doing river walks on the Naperville Riverwalk this Thursday, April 7th at 7:30 p.m. We also have a STEM event at Albright Middle School, and I apologize, I don't have the time for that. That is at 6:30 p.m. This weekend we'll have a public night at our observatory starting at 8 p.m. All these things are dependent on clear weather, and I think we don't have clear weather on the forecast currently. The STEM events are usually not weather dependent. April 11th is stargazing at Plum Library in Lombard. The 16th, we're back to doing solar Saturdays. Those are on the Naperville Riverwalk, 2 across from the library. Those are from 9 a.m. until noon. Astronomy Fundamentals on the 19th, 7 p.m. That'll be streaming again. That'll be by Larry John. April 23rd is public night at our observatory. The nights or the days are getting longer, so that'll start at 8:30 p.m. When visitors can come out, and then we have a members only night at our observatory on the 30th, and that the gate is at 8 p.m. for that. And we have also on April 30th a STEM day at the College of DuPage, and that's from 10 a.m. to 4 p.m. So a lot of events. Things have been quiet, but we're getting back out there now. So need volunteers for all these. Thank you. If you're watching on Facebook, you can just comment in the comment section on the video, and Chris will feed those to our speaker tonight. And if you're watching on our website, you can email questions@naperastro.org, and Chris will be checking his email too, and he'll feed those to our speaker as well. Tonight, our speaker is Bhasker Moorthy. He's going to be talking to us about when galaxies collide. So Bhasker is a professor of astronomy at Harper College. He has a bachelor's in physics and astronomy from the University of Washington and a PhD in astronomy from New Mexico State University. And his dissertation was on central bulges of spiral galaxies. And he works with, he's worked with Roger Coleman. A lot of us know Roger Coleman. He's a member at Harper College. So Bhasker, if you are ready, we'll turn everything over to you.
Yeah, thank you. I just unmuted myself and I'm going to share. So is it okay if I share my
Yes,
screen?
absolutely.
All right. I'm going to share PowerPoint file. Okay, you should be able to see that. So it's great to be here. This is my first Naperville Astronomical Association meeting. I've been at Harper for 15 years. I've heard quite a bit about your club from Roger, and I'm glad I finally got the chance to join you. So yeah, I'll be talking about the different types of galaxies, the basic properties of galaxies, and what happens when two of them collide. So here's a famous Hubble Space Telescope image of two galaxies colliding. Let me start with our own galaxy, the Milky Way. So this is one view of it. So since we live inside the galaxy, it's actually difficult to study its structure. So we live in the disk of the Milky Way, and when we look towards the center of the Milky Way, it looks a bit like this. So all of the stars you're seeing are part of the Milky Way. And it's hard to tell that there's a bulge towards the middle. We see a lot of glowing clouds and lots of dust obscuring the view towards the center. Here is an all-sky image of the Milky Way. So it's centered on the galactic center. And here you can see the bulge a little better. This is still the Milky Way in visible light. Dust is still a huge issue. It's hard to look at the central region and much of the disk because of all the dust in the way. But if we switch over to the infrared, we can look through much of the dust and study the structure of our galaxy in more detail. But it's nice to be able to see a whole bunch of other galaxies as well here. And once we've, having done that, having looked at a whole bunch of other galaxies and having studied the structure of our own galaxy, we can make models of our galaxy, the Milky Way. So here is one such model showing our location in the disk and also showing the bulge at the center. Okay, here is another spiral galaxy. Those of you that have been part of the club, those of you that are in the citizen science game or own your own telescope, you might have seen this with the backyard telescope or maybe with the larger telescope. Here is the other large spiral galaxy in our neighborhood, the Andromeda Galaxy, also known as Messier 31. Ours is a large galaxy. This one's even larger. And when you look at a spiral galaxy that's not perfectly edge-on, that's face-on or at moderate inclination, you can tell that it's got a largely featureless bulge and a much more interesting disk. There seems to be much more going on in the disk than in the bulge. One of the things you can notice is that the disk looks blue, or at least parts of the disk look blue, while the bulge looks yellow, orange, or red. The colors of the regions of a galaxy can tell us quite a bit about the evolution of that galaxy and the types of activity that are taking place in that galaxy. To understand why, let's look at a couple of places inside our own galaxy. So here is a star cluster. This is another well-known object to members of astronomical associations. This is an object that's easily visible to the naked eye. It's called the Seven Sisters. It's the Pleiades star cluster in Taurus. It's visible this time of year. And with the naked eye, someone with good vision might be able to see 7 stars. Most people can see 6 stars. In reality, there are thousands of stars inside of this cluster. And the brightest ones appear blue. But again, I said there are thousands of stars inside this cluster, which means the vast majority of the stars in this cluster are actually not bright and blue. They're actually the really, really faint stars that are seen in this field. And most of those are actually red, orange, and yellow. Now, let me show you a different type of star cluster. So the Pleiades is an open cluster, and here is a globular cluster. So this is a much denser cluster of stars. There are plenty of globular clusters that you can see with a pair of binoculars or a small telescope. From the northern hemisphere, a couple of popular ones to look at are the Hercules cluster, M13 and M92. Omega Centauri is visible in the southern, only from the southern hemisphere or from pretty close to the equator. It's slightly larger than the Hercules cluster, but they pretty much all look the same. So it's called a globular cluster because it does look like a globule. It's round, nearly spherical. And the stars are much, much closer together than in an open cluster. Okay. But what's, to me, most interesting about a globular cluster is what it doesn't have. It doesn't have the bright blue stars. The light is not dominated by luminous blue stars. Now that's significant because that tells us something about the age of this cluster. Let me go back to the Pleiades. So these bright blue stars, these very luminous blue stars, turns out don't live very long. They only live for a few 100 million years, or maybe even less than 100 million years. That's a very short amount of time in astronomy. And the faint red, orange, and yellow stars will live much, much longer. But the thing about a cluster of stars is all of the stars in the cluster formed out of the same cloud of gas at the same time. So they all have the same age. The fact that this cluster still has the bright blue stars means that it's extremely young. So this is a young cluster. We know that because it still has the bright blue stars. The yellow, orange, red stars can hide because they're really faint. They're not very luminous. But the bright blue stars cannot hide. So if you don't see them, so the fact that we don't see the bright blue stars in the globular cluster tells us that they're not there. They're dead. They're long gone. Globular clusters in our galaxy, the Milky Way, are billions of years old. They're over 10 billion years old. All of them in our Milky Way seem to be very, very old. So to recap, if you're looking at a part of a galaxy where you only see yellow, orange, and red stars, that part of the galaxy must be old because it's not forming new stars. And if you're seeing a part of the galaxy that looks blue, like this part of the Andromeda Galaxy, that means it contains young stars. It doesn't mean it doesn't contain old stars. It could still contain old stars because unlike a star cluster, a galaxy could have formed stars over time. All the stars in the galaxy didn't necessarily form at one time. So a disk could contain old stars, but it also contains young stars. We know that because it contains bright blue stars. The light here is dominated by blue stars. That means it still has the very young luminous blue stars. And the bulge of the galaxy, the fact that it doesn't look blue means that the blue stars are long gone. And so the bulge must exclusively contain old stars. In this image, you can see two other galaxies. So these are two other companions. These are two companions of the Andromeda Galaxy. These two happen to be elliptical galaxies. They're not spiral galaxies like the Milky Way and Andromeda. And you can see that they look yellow or orange or red. Astronomers are lazy. We mostly only talk about two colors, blue and red. So if it's not blue, it's red. So yellow, orange, and red all are considered blue. Are all considered red, just for simplicity, okay? So we'd say ellipticals and bulges are red. That means they only contain old stars. Disks contain young stars because they look blue, at least in some regions. Now, the other thing that we find in our own galaxy is a whole bunch of glowing clouds of gas that contain lots of dust. These are star-forming regions. So here's the Orion Nebula. It's also visible at this time of year. This is one of the best studied star-forming regions. So it's glowing pink or red because of hydrogen gas, and it contains lots and lots of dust. It turns out dust is extremely important to astronomers for two main reasons. Number one, you and I, and the entire Earth, is made of dust. So we are stardust. So the elements that are found in our bodies are mostly water, right? So the water is hydrogen and oxygen. The other thing astronomers are really lazy about is if it's not hydrogen or helium, it's considered a metal. At least people that study galaxies, things that are heavier than helium, they're called metals. So oxygen and nitrogen and carbon are considered metals. Astronomers know what a metal actually is, but we call them metals because they're formed deep in the cores of dying stars. Unlike the hydrogen and helium, which goes all the way back to the Big Bang. So if you take the human body, the hydrogen in the water that makes the most of your body is incredibly old. It's 13.8 billion years old. It's as old as the universe. So if you think that you're nice and youthful, only 20 years old or 30 years old or 40 years old, much of your body is 13.8 billion years old. It's just, the stuff's just been moved around a lot. And the oxygen we inhale, the oxygen in the water in our bodies, the carbon in our DNA, the calcium in our bones, the iron in our blood, all of that is at least 4.5 billion years old because it all existed when the solar system was born. The Earth and the Sun, they were all born around 4.5 billion years ago out of a cloud of gas like this one. So when we look at a spiral galaxy, we see nebulae like this. So when you look at, for instance, the Sombrero Galaxy, because it's nearly edge-on, it's hard to see the glowing red and pink regions, but we do see dust. We see plenty of dust. Oh, and the other reason dust is important to astronomers is without dust, stars don't form anymore. So dust keeps the cloud nice and cold. It insulates it from the heat and light from the surrounding stars. And once the cloud gets cold, then gravity takes over and the cloud can contract, fragment, and form thousands of stars. And so we only see this happening in a spiral galaxy inside of the disk. So when you see dust, that means stars can form there. And here is another spiral galaxy. This one has the glowing pink clouds, and you can see dust here and there. This one's nearly face-on, so it's actually hard to see the dust sometimes in a face-on galaxy, but you can notice the glowing pink clouds very well, and you see the blue regions. So it's got the young stars because you see blue regions. It's got dust, which forms new stars, and it's got the glowing pink clouds where stars are forming today. They're being born. And here is an elliptical galaxy. Look how boring it looks. It completely lacks all of the things that make a spiral galaxy beautiful. It doesn't have the spiral arms. That's what makes a spiral galaxy a spiral galaxy. So no spiral structure here. It doesn't contain the blue regions. So no blue stars means it only contains old stars. It's not forming new stars. The reason it's not forming new stars is it doesn't contain dust and it doesn't contain the cold gas that can turn into new stars. And because it's not forming new stars, it doesn't have those glowing pink and red regions. So it's just a very smooth ball, diffused ball of old stars. Again, we would call this red. Clearly, this doesn't look that red. You might call it yellow, but for simplicity, we just like to think of blue versus red. So ellipticals and bulges, reddish, which again includes yellow and orange, and disks of spiral galaxies can be quite blue. Now here's a close-up of one of the dwarf galaxies around Andromeda. Andromeda is Messier 31, number 31 in Charles Messier's catalog. Number 32 is its companion M32. So a dwarf elliptical galaxy. So again, the fact that it looks yellowish and featureless means that it doesn't have all of the action taking place in a spiral galaxy. And the third main type of galaxy is an irregular galaxy. So it doesn't have spiral arms, it doesn't have a flat disk like a spiral, and it's not elliptical or round, nearly spheroidal like an elliptical galaxy. So it can have any shape, and so it's just called an irregular galaxy. Now, in terms of the types of stars we find, the irregular galaxies are actually more similar to the disks of spirals, because we do see blue regions. This is our companion, the Large Magellanic Cloud, one of the two clouds of Magellan. And you see blue stars here and there, and you see the glowing pink clouds. So that means irregular galaxies typically form new stars, just like disks of spirals. And so far, I don't think I've seen any questions come in the chat. Let me pause and take a look. Okay, I'm seeing nothing in the chat yet, so I'll look for questions. If you do have questions, please put them on Facebook or via email or however you were asked to, and I'll be getting those, and once in a while I'll stop and respond to those. Okay, so let me back up. Yeah, here's the Large Magellanic Cloud again, irregular galaxy. Here is a different irregular galaxy, also has a lot of blue stars. Again, that doesn't mean it doesn't contain the faint yellow, orange, and red stars. All galaxies started forming over 10 billion years ago. So all galaxies, you could say, are old, but some have been evolving during the last 10 billion years, while others have not been doing too much. They've just been sitting there. At least there's been no evolution in there's been no new star formation in many of them. Okay, so this one's got blue stars, which means it's still forming new stars. Here is a dwarf spheroidal galaxy. Now, it's hard to see where the galaxy actually ends. Dwarf spheroidals are the faintest galaxies in the universe. They have the lowest luminosities of any of the galaxy types. In fact, they're very difficult to see beyond the local group. We only see them in our neighborhood because they're so faint. Now, okay. I'm sorry, I'm having issues. Okay. Now, by the way, I need to point out that the galaxy in this image is not this thing over here. That's a star, okay? If you look towards the central portion of the image, you see an overdensity of stars. That's the galaxy. Again, I pointed out that it's hard to even see the full extent of the galaxy. Basically, if you look at the bottom left of the image, you count fewer stars than if you look towards the center of the image. That tells us there's an overdensity of stars. Most of the stars are not going to, if this galaxy are not going to be visible in this image, you have to take a much longer exposure image to be able to see them. They're just very faint. They're those red and orange dwarfs. Okay, so those are the three main types of galaxies. Ellipticals, spirals, and irregulars. Okay, ellipticals are really part of a broad family of galaxies called spheroidals. There are big ellipticals, small ellipticals, and dwarf spheroidals as well. What they all have in common is they don't contain blue stars. They only contain yellow, orange, red stars, which means they're not forming new stars. Okay, now let's look at galaxy collisions. Things are going to get much more exciting. Let's start with a beautiful, relatively nearby spiral galaxy, okay, the Whirlpool Galaxy. Nearly perfectly face-on spiral galaxy, okay? It's got everything you expect in a spiral. It's got the spiral arms. You see the bulge, which looks yellower than the disk. You see blue stars in the disk. You see the dust, and you see blue stars, and you see the glowing pink and red clouds, those nebulae that form new stars. Okay, so this galaxy looks like it's got nothing disturbing it, nothing bothering it, right? It looks perfectly just pure and untouched. Well, that's not the case at all. In fact, if you stare at it long enough, you might start noticing that it's not perfectly symmetric. It looks a bit flat over here. It's got some warps in its spiral arms. The spiral arms over here, they don't just continue in like a nice spiral pattern. They appear to be kind of flattened over here. So that's a warp, but I'm not showing you the entire image. So here is more of the same image. I cropped it. This galaxy is actually eating its companion right now. So the Whirlpool Galaxy is called M51, Messier 51. Its companion is NGC 5195. NGC stands for New General Catalog. It was new about 100 years ago, not so new anymore. So this galaxy is eating its companion. That's called galactic cannibalization. Galaxies eat each other. Okay, and in the process of getting eaten, the smaller galaxy has been deeply disturbed. It doesn't have normal types of structure at all. We see some dust, but otherwise it looks very, we would say, peculiar. It's a peculiar galaxy. You wouldn't call it a spiral or elliptical, but unlike an irregular, it doesn't have blue stars either. It just looks like a big mess. So that's what we call a peculiar galaxy. It's not one of the normal types. Here is another beautiful spiral galaxy, okay? Messier 81, okay? Again, seems to be perfectly just uniform, seems to be isolated, nothing seems to be bothering it, okay? But then Messier 82, which presumably is nearby, considering it's the next one in the catalog, looks anything but beautiful and symmetric and uniform. It just looks like one chaotic mess. It's violently disturbed. It's a highly peculiar galaxy. So why is that? Why is M81 the lucky one, while M82 has been horribly disturbed? Well, here are both the galaxies together. They're not that far apart. Okay. Turns out M81 is messing with M82. This is action at a distance. So the two galaxies haven't fully merged together, but one galaxy is actually bothering the other galaxy. The technical term for this is galaxy harassment. Galaxies harass each other. They cannibalize each other, and before one's eaten another one, it can actually mess with it from a distance. It can harass it. Here is a radio image showing M81 and M82 and a third galaxy. Now in radio waves, so far I've shown you optical images, visible light images, one infrared image. Now here's a radio image. In radio, we can look at hydrogen gas, which can extend way beyond the stars of a galaxy. So you can see that the hydrogen gas in these three galaxies has already started interacting. They're not three isolated galaxies anymore. They're already starting to merge and interact. So that we wouldn't know if we looked only in visible light. So it helps to look at all the different wavelengths of light, from gamma ray to radio, to get a complete picture of galaxies. So Jim tells me we have a couple of questions, so I'll pause and let Jim let me know what they are.
Sorry about that, Bhasker. I thought I sent the message to you. I sent it just to Jim. So we have a couple of questions. I'll ask Jim's first. Do galaxies need to be, and they're also relatively related, do galaxies need to be a certain size or number of stars or a certain age before it becomes a spiral?
Yes, the short answer is yes. There are spirals at different sizes. So there are smaller spiral galaxies than the Milky Way, quite a bit smaller, and there are spirals that are larger than the Milky Way. But even the smallest spirals are larger than the dwarf spheroidals and the dwarf ellipticals. So the smallest galaxies in the universe are dwarf spheroidals, and then there would be these dwarf ellipticals, which are a different class, and some of the dwarf irregulars. Okay, the Large Magellanic Cloud is an irregular galaxy. There are irregulars that are much smaller even than that, and all of those are smaller than even the smallest spiral galaxies. So there is a sort of a minimum size for a spiral galaxy.
Okay.
So it just has to be a certain size before we start seeing spiral structure inside of it.
Okay, and then, like I said, these are all kind of related to the size. So Dave Martin asks, define dwarf, please. And then kind of my own question, is the size of galaxies based on star count, or is it based on mass, which may or may not be in the form of stars?
What I've described so far is just based on what we call morphology, which is just appearance. It's just based on the structure. But all of these things are related to each other. So, spiral versus elliptical versus irregular, those are just described based on the shape. Okay. And in astronomy, usually things are named by the first few people that have seen these things. Things are often named by the people that discover them. And quite often, when things are discovered, we don't know that much about them. But the names stick, people start using these names, and later on it turns out that the initial hypotheses pertaining to these objects were completely wrong, and so the names can be very misleading. They might not actually tell us anything at all about these objects. So with stars, this is very much the case. Like dwarf doesn't often even mean anything. Like a white dwarf is neither white nor a dwarf. A planetary nebula has nothing to do with planets. So names can be very misleading. But in the case of galaxies, people like Hubble did have some wrong ideas about galaxies, but the names are still okay. They're not terribly misleading, okay? So they were named just based on appearance, how they appear. But having said that, they correlate with mass as well. So the most massive galaxies in the universe are either spiral or elliptical. So there are giant elliptical galaxies. In fact, the most massive galaxies in the universe are the cluster dominant ellipticals. So massive elliptical galaxies inside clusters of galaxies. I'm going to show you one or two of those. And so there are massive ellipticals in dense clusters of galaxies. And after that, the most massive galaxies would be spirals. Okay, so there can be very massive ellipticals and very massive spirals. And then there can be slightly lower mass spirals, etc. And then smaller than the lowest mass spirals would be all of these other types, dwarf irregulars, dwarf ellipticals. And again, the lowest mass galaxies would be the dwarf spheroidals. And then number of stars also would correlate. It's very difficult to count stars in a galaxy. Again, in a dwarf spheroidal, we're not seeing all the stars. We're only going to see the brightest stars, even with the most powerful telescopes and the longest exposures. So it's hard to know, hard to get a full tally of the stars. But there's something called an initial mass function, which seems nearly universal. And all it tells you is when stars are born, what fraction of the stars have large mass, high mass, what fraction of the stars have low mass, etc. And it seems to be nearly universal. Whenever we see stars being formed, we find a lot more low mass stars than high mass stars. So you'll find more of the smallest red stars, the faintest red dwarfs, red main sequence stars. Those will be the majority of the stars. And after that, you'll have the orange ones, which are slightly more luminous, and then the yellow ones, which are slightly more luminous, stars like the sun and so on. The bright, massive violet stars, violet and blue stars, there are very few of those. Those are really rare. Okay, and so when we look at galaxies, we usually only see the brightest stars, but we can infer that they must contain a lot more of the faint red, yellow stars, yellow, orange stars as well. Okay, so there could still be some mysteries out there. Let's say the initial mass function of dwarf spheroidal galaxies is different than for spiral galaxies, then maybe we don't have a full accurate count of the number of stars that they have. But if they do have roughly the same proportion of low mass and high mass stars, then we can try to get an estimate of the total numbers of stars. And again, yeah, we'd find more stars in the massive ellipticals and massive spirals than in the smaller spirals and so on. Okay, so everything is correlated. The appearance, the types, the number of stars, and the total mass. And of course, in most galaxies, most of the mass is actually in something called dark matter, which I'm not going to get into in this talk, but I'll mention it now. Recently they found a galaxy or two where they thought there is no dark matter. That was surprising because most galaxies do seem to have mostly dark matter, but still, there is a correlation between the number of between the luminous mass in a galaxy and the total mass of the galaxy. So if it's very massive, then it probably contains, if it's got a lot of stars, it probably also contains a lot of dark matter and so on. Although the proportion of luminous matter to dark matter can be different for different types. So long answer to those questions, but I'd like to be honest and detailed. Anything else?
At this time, no.
Great, thank you. Okay, so moving on. Now, here is another deeply disturbed galaxy, severely warped. So if you look at the spiral arms of this galaxy, it looks like someone reached in and started pulling the arms apart. So this galaxy would be nearly edge on, but then it looks like one of the arms got pulled up while another one got pulled down. So why is this? Well, here also I've cropped the image. I'm not showing you the entire image. On the left is the rest of that image. You see what's called a tidal tail, a long tail that's attached to that galaxy. So what happened is another galaxy plowed right through this galaxy. So this galaxy underwent a merger. And on the right is a pair of galaxies that's undergoing one of these mergers now. And you see a long tidal tail here as well. And when we look at the cores of these galaxies, you can tell they look deeply disturbed. They don't look like normal spirals, ellipticals, or even irregulars. Okay, let's look at some more examples. Here is a famous pair of merging galaxies called the antennae. Now, this looks particularly luminous. When we look at the central portion, it looks very bright. We're seeing extremely bright, glowing clouds of gas and lots of dust. This is what we would call a starburst galaxy. It's bursting with star formation. So the disk of the Milky Way forms new stars, right? So when you see dust and glowing clouds, that's an indicator of star formation. But the Milky Way is not forming stars that actively. It takes a long time for stars to form. A star like the sun would have taken about 30 million years to form. Many stars form at once. But it turns out that if you were to average that out, the Milky Way forms about one star per year. Okay, so it forms many at a time, but many stars are, but each one takes a long time to form. So on average, you could say the Milky Way forms about one star per year. Now, a starburst is forming thousands of stars per year. So it's got thousands of times as much star formation going on as a normal spiral or normal elliptical. And we find starbursts to be deeply disturbed. So it appears that galaxy collisions seem to trigger big bursts of star formation. Here is another pair of galaxies that are merging. Again, this one looks very blue, indicating lots of new stars that have been formed, also a starburst. And here are 5 galaxies that are coming together. A couple of them have already started merging, and the others are about to join the party. Okay, so another famous group of galaxies. Okay, now I'm going to show you how galaxy collisions actually ended up producing a large spiral galaxy like the Milky Way. So galaxy collisions aren't just pretty to look at and kind of interesting to contemplate. They were integral to the formation of large galaxies like the Milky Way. So here is a video made using a numerical simulation. So a supercomputer simulation of galaxy formation. So initially, we see a whole bunch of small galaxies. Probably even can't even tell that these are galaxies yet. We're just seeing little clumps, okay? And they're starting to collide. And you see a spiral galaxy emerge, right? Initially, there was no spiral structure, but already you see a small spiral galaxy having emerged close to the center. And then there's another spiral galaxy coming by, and a third not so spiral galaxy. And these two spirals are colliding together, and that third one might also join in on the action. And after the collision, once again, new spiral arms are forming. So now we have a large spiral galaxy having formed from the mergers of all of these small clumps. And 2 of these large spiral galaxies now are about to collide. And it's a big mess for a while. It would be a starburst. So the gas from the 2 spiral galaxies would have been colliding violently and bursting with new star formation. And in this case, there was still plenty of gas left over to form a new disk. So we think the bulge of a spiral galaxy is formed from the stars that collided together from the 2 galaxies that merged. And then the gas that's left over, if there's enough of it, can form a new disk. So the disk of the Milky Way probably formed after several collisions. And it kept growing as we kept colliding with additional galaxies. There isn't really anything more to this simulation, so I'll just let it run to the end. It's maybe there's more to it, but nothing new is going to happen. So let's move on. Oops, let me go to the next slide. So the Milky Way to this day is eating companion galaxies. It's not done cannibalizing galaxies. So much of the action you saw in that simulation took place over 10 billion years ago. So if you could go back in time, 11, 12, 13 billion years, but if you stayed in this part of the universe, you would find, you wouldn't find a large spiral galaxy. You would find a whole bunch of galactic clumps that are colliding together. And by 10 billion years ago, so about 3.8 billion years into the universe, already there would have been a decently large spiral galaxy here. But that galaxy, so the Milky Way, has been eating other galaxies during the last 10 billion years, and it's been continuing to grow. And after every one of these collisions, the stars from the eaten galaxy slowly spiral in and make their way to the bulge, we think. So my PhD thesis was on spiral galaxy formation. So it became pretty clear during those 6 years that I was doing my master's and PhD, not just through my work, but through the work of all of us in that field, that galaxies, bulges really form through mergers. And so by eating up companion galaxies, bulges form and grow. So after a collision, the stars make it into the bulge, and whatever gas we might have eaten from the companion galaxy can be added to the disk, grows the disk. Okay. And if the two galaxies are almost equally large, initially the disk will be completely destroyed, but then if there's still gas left over, the gas can settle into a new disk. Disks need to be nice and stable. You need to have nice rotational motion. Things need to be nice and calm for a disk to form. So it takes a while to form a new disk. So what you see on the right is theory. So this is from numerical simulations suggesting what might be happening when the Milky Way, as the Milky Way eats the Sagittarius Dwarf Spheroidal Galaxy. What you see in the left is basically one image and then data from other images. The yellow squares show where they've done deep observations to try to figure out the extent of this galaxy called the Sagittarius Dwarf, whose core is now pretty close to the center of the Milky Way, but whose innards, or whatever you want to call them, debris, are scattered all over the place. So our galaxy is still eating and digesting this dwarf companion. Now there's another question. How correlated is that motion to planet formation around a star? Is there any? So planets form when stars form. So the sun formed 4.5 billion years ago in a protostellar disk. So initially you have a big cloud like the Orion Nebula with gas and dust. That cloud is going to fragment, and every one of those tiny fragments can form a cluster of stars. We actually think that stars probably don't form individually, they form in clusters. Now in this Milky Way today, in the disk of the Milky Way, we think they're formed mostly as open clusters. That's why we have young open clusters in the disk of the Milky Way. But after one of these major mergers, we think globular clusters can form. The Milky Way hasn't had one of these dramatic major mergers in about 10 billion years. That's why the globular clusters are all old. Anyway, so stars are born in clusters, which means the sun probably has long lost companions that it formed with. It probably was part of an open cluster 4.5 billion years ago. But as the sun was forming, okay, in a protostellar disk, planets started forming in that disk as well. So we call that the protoplanetary disk. And when we're focusing on the planets. And so how correlated is that motion? So if the question is, we see disks in spiral galaxies, and we also see disks on much smaller scales forming around baby stars. Those two are not correlated. So like the disk that the sun and the planets formed in does not have any correlation to the Milky Way's disk. If that's the question, no, there isn't anything there. But yeah, star formation means planet formation as well, because planets form with stars. So in a starburst galaxy, we would be expecting lots of planets to form too. But planets are very difficult to see, right? 30 years ago, We didn't even know of extrasolar planets. We were just starting to discover them 27 years ago. And and we only see them in our part of the Milky Way galaxy. We can't see planets in other galaxies, but we would expect planets to form when stars form. Okay, now, here is an elliptical galaxy. Again, elliptical galaxies should look completely featureless. They should be smooth. They should contain no blue stars, no spiral structure, no glowing pink and red clouds, and no dust. But this one contains dust. That's odd. Elliptical galaxies shouldn't contain dust. So why does this one contain dust? Well, it probably ate it from a spiral. So elliptical galaxies sometimes appear to eat other galaxies. And sometimes it takes a while for that material to get fully digested or to just fade away. So this elliptical galaxy must have recently eaten a spiral. Now, here is a galaxy that looks deeply disturbed. And when we look at the central portion, we actually see two cores. Okay? That means the two galaxies were merging together, haven't fully fused together to form a single bulge. The stars haven't fully come together. There's still two distinct cores at the center. So if we were to come back to this in 1 billion years, we would expect these to have merged together fully. Okay. Here is another elliptical galaxy, which looks very unusual for an elliptical because it's got dust. It's got a big veil going across it. This one also is an active galaxy. It's got radio jets, and jets that might even be emitting some visible light. This is actually a composite image showing radio and visible. So most of the jet activity is actually in the radio. So this is an active galaxy. Active means there's a black hole in the center that's eating up a lot of gas, and some of that debris is getting directed into jets. So this elliptical also must have eaten a spiral. That's where all the dust must have come from. Okay, ellipticals seem to eat spirals sometime. And here is a giant cluster of galaxies. Now, if we had taken a low exposure image, we would have just seen one big fuzzy galaxy over here. We would just call that a massive elliptical galaxy. That would be one of these CD galaxies, a cluster dominant elliptical. But when you look at it in more detail, you can see that it's actually got subcomponents. It's got all these galaxies inside of it that it had for lunch. And it hasn't fully digested yet. That means all of these things that look like they're just outside the galaxy, they're going to be dinner. They're also going to get eaten. Okay, so at the centers of galaxy clusters, we see evidence of lots of merger activity. So ellipticals probably formed also from collisions. So how do we get the massive ellipticals? Well, they probably ate smaller galaxies, or a whole bunch of small ones merged together to become one big one. Okay. All right. So how about our own galaxy then? Is it going to undergo another major merger in the future? Answer is yes. It's not done. Turns out in clusters of galaxies, there aren't major mergers happening anymore. If you look at these galaxies inside the cluster, the big ones are all moving too fast to actually collide together. We call that velocity dispersion. They have high velocity dispersion. They're actually moving too fast to collide together. They're going to keep missing each other. But in groups of galaxies, and we live in the local group, we live inside of a group, the galaxy speeds are still low enough that we expect there to be collisions today and in the future. And inside the local group, we think that there's going to be one massive merger. The Andromeda Galaxy is even larger than the Milky Way. Today, it looks harmless. Okay, so this is a simulated image. Normally, when we look at Andromeda, we don't see this many stars in the sky. If we could, Andromeda would look a little brighter. So this simulated image shows the stars of the Milky Way plus Andromeda in the background. And then I'm going to show you a series of images by Roland van der Merel and his team at Space Telescope Science Institute and a couple of collaborators. This is going to project this into the future. Turns out the Andromeda Galaxy is moving towards us. So in 2 billion years, it's going to look much more menacing. It's going to be much larger in the sky than it is now. Okay, it's going to be much, much, much larger than the moon. It will be ominous. It'll look quite scary. In 3.75 billion years, it'll be enormous. It'll take up half of the sky, and it will be much more warped than it is today. And it basically is about to start colliding with our galaxy at that point. So 3.75 billion years, now things are going to happen pretty fast, okay, on cosmic times. Still pretty slow by human standards, but 100 million years later, you're going to see just a giant mess. You're not going to be able to see where the Milky Way ends and Andromeda begins. The collision is fully underway. They're colliding together. And this is a starburst galaxy, just bursting with new star formation, okay? The two galaxies are merging together. The merger is triggering huge bursts of star formation, okay? Now, what's going to happen at the end? Well, if you think about it, the stars from the collision will make it towards the center. The bulge will get larger and larger. The two bulges of the two galaxies will come together and turn into one giant bulge. The other stars will also, keep getting added to this. So it's going to be like one giant bulge. Okay. The stars are basically a giant bulge. Okay. New stars are being born. These bright blue stars, they don't live very long. They die soon after they're born. Eventually, the dust fades away. You don't see the dust anymore. So you only see yellow, orange, and red stars. And the two distinct galaxies emerge together, and things are looking less bright over time and starting to fade away. There is still two giant bulges in the sky, and everything else is fading away. This is 5.1 billion years into the future. Around that time, the sun's going to start dying. So lots of chaos happening 5 billion years from now. The sun would have become much hotter and brighter long before then. So Earth will not be habitable, won't be anything like it is today. So if there's still going to be life forms on the Earth, they'd be wise to migrate further out into the solar system where it's going to be cooler, unless they like it hot. But eventually the sun's going to die too. And after the sun is gone, long after that, the two galaxies, the Milky Way and Andromeda, would have completely lost their distinct identities, and they'll just be one big, smooth, featureless galaxy. Now, if I could see you all, I would ask you, what type of galaxy is this? I think you would all agree that this is what we call an elliptical galaxy. So what we've learned over the last 20 years is that when two large spiral galaxies collide together and all the gas in the two galaxies gets consumed in these starbursts, and there's no gas left over to form new stars, to grow a new disk, you actually end up forming an elliptical galaxy. So an elliptical galaxy is the ultimate endpoint of the collisions of many, 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 many galaxies. So an elliptical plus an elliptical, when they collide together, you'll have another elliptical, because ellipticals can't form new stars. So you have old stars and old stars just merging together, big ball of old stars. Two spirals slamming together can make an elliptical. Elliptical plus spiral smashing together can make another elliptical. So everything eventually, after lots of collisions, will probably lead to elliptical galaxies. So it turns out that these ellipticals that seem to have nothing to do with the Milky Way initially, these seem like a completely different type, can actually form from two spirals colliding together. So finally, let me show you what this team has produced along with these simulated images. Here's an animation of this collision. I hope you can all see this. It looks like it brought this up in a browser. If you can't see it,
We cannot see that.
Okay, I don't know why I did that. I'm so sorry. Let me stop sharing here. I'm going to pause this. You will be able to see it in just a minute. I'll stop sharing PowerPoint and I'll share a browser and you will be able to see this. Okay. Okay. You should be able to see this now.
Yes.
It just shows the Milky Way. And we're going to just speed up time. So 500 million years from now, 1 billion years from now, the Milky Way still seems isolated enough that it's safe. There is Andromeda, and there's a third member of the local group, M33, the Triangulum Galaxy. And the Milky Way and Andromeda approach each other. They check each other out. They don't just merge right away. They do a little dance. And then they plow right through each other. Now, there's a lot of space between the stars inside a galaxy. So stars in the Milky Way will not collide with stars in Andromeda. They'll just slip right past each other. But gravity will bring them back for a second collision and a third collision. And eventually, they will turn into one starburst. And after all the new star formation's done, and things settle down, about 7 billion years from now, we'll find ourselves inside a giant elliptical galaxy. Now, that third galaxy, M33 Triangulum, appears to have been spared. It's going to get eaten eventually, too. All the galaxies in the local group pretty much are going to end up inside this giant elliptical galaxy that some people call the Andromeda Galaxy, just Milky Way and Andromeda merged together. So that concludes my talk. Feel free to ask any questions that may have come up.
Okay, Bhasker, don't see any questions. Let me check my email real quick. Oh, wait, here we go. So David Barkus is asking, how would you summarize the fireworks galaxy? Is the appearance the result of a recent collision?
The fireworks galaxy?
Yes.
I'm not familiar with the fireworks galaxy. Yeah, I can look it up real quick or something. I don't mind doing that real quick, but I don't know which galaxy is the fireworks galaxy. Fireworks galaxy. NGC 6946. Okay, this looks like a spiral galaxy. I'm still sharing this, so I'll just, yeah, this is a spiral galaxy. It looks,
yeah, so he was asking, is the appearance the result of a recent collision?
well, okay, so what are some signs of a collision? If it's really a massive collision, then, you know, it loses all of its identity, right? You don't see any structure in it at all. You just see a giant mess. It looks peculiar. If it's been a minor merger or something, you might see tails or warps. This one seems, you know, not too disturbed or anything. You know, the spiral arms maybe ends abruptly, but not necessarily. I mean, it doesn't look like it's undergone a recent merger. There's still pretty clear spiral structure and it looks fairly symmetric. So yeah, looking at this, I wouldn't say it's undergone a very massive recent merger or even like a big interaction, any serious harassment or anything like that. Seems just like a normal spiral to me.
Okay. David Martin asks, what is the largest elliptical that we know?
I don't know. I'm not on top of like stats when it comes to the most massive galaxies, but it would definitely be inside a galaxy cluster. So the one that I showed you, Abel, whatever, that's one of the bigger ones I've seen. So Abel is an astronomer that has a lot of galaxy clusters named after him. So there's an Abel catalog of galaxy clusters. I wouldn't be surprised if the most massive galaxy known is inside one of these Abel clusters. But yeah, I'm willing to bet that it's a massive elliptical inside a cluster, one of these CD galaxies, cluster dominant galaxies, but I don't know which one it is.
Okay. Bill Pardue asks, would events like supernovas, etc., within an elliptical cause any new upticks in star formation, or is everything really just burning out slowly?
Yeah, it would not cause new star formation. Now, there are two main types of supernovae, type 1a and type 2. So type 2 supernovae are the explosions of massive stars. Okay, so very massive stars, the violet and blue main sequence stars, they turn into red supergiants eventually, and then they explode. Now, those types of stars don't live very long. So we won't find those in ellipticals, right? So ellipticals only contain old stars. So that means they can't have type 2 supernovae. They're only found in irregulars and spirals. Now, the other main type of supernova is the type 1a supernova, where you have the collision of two white dwarfs. Ellipticals do have plenty of white dwarfs, and so we would expect there to be type 1a supernova in ellipticals, and we do see them. But all the other conditions required for star formation are not there. So the shock waves from a supernova might trigger new star formation if the other ingredients for star formation are present. So you do need cold gas and you need dust. You don't have the cold gas and dust in ellipticals to form new stars. And so no, we don't expect there to be new star formation in ellipticals.
Okay, great. I think we are at our, every time I say we're at the end of our questions, one always pops up. So I always give it a few seconds here and I double check my email, but I think we are at an end for the questions. Thank you very much, Bhasker. Jim, are you ready to take back over?